In this part, we want to figure out what the layout problem formally is. And for that, first we have to have a look at what graphs are and how we can represent them. So probably you know what a graph is, but the definition is a graph is a tuple of a set of vertices and a set of edges. The vertices are just entities. You can imagine them as people in a social network. And every edge is a tuple of vertices. You can imagine them as connections. So for example, person V1 knows person V2, then there is an edge between them. Now how do we represent this graph? Well, the easiest form is we just take this set representation here, we write down what are our vertices V1 to V10, and we list all these tuples of edges, and we get a representation of our graph. But this is not very helpful. If I just look at this, then I cannot really make out a lot of this graph and what structure it has. What's a bit more useful is the adjacency list representation. So we list all our vertices, and for each vertex, now we have a list that contains all its neighbors. So here we have an edge between V1 and V2 and an edge between V1 and V8. So for V1 we list V2 and V8 in the adjacency list. Now here I can already read a bit more. For example, we can see that V1 has 2 friends and V8 has 6 friends. But we cannot see a lot about the global structure. This is only very local information. So having a good drawing can help you a lot to analyze what kind of data you have. And also it looks nicer. But social networks are not the only data that we use for graphs. In general, graphs are mathematical representations of real physical and abstract networks. For abstract networks, like I had in my example, we have social networks, but it could also be communication networks, phylogenetic networks, metabolic networks, even UML diagrams. That's also just graphs. And all of those, you get information out of it by drawing them. And physical networks, you have metro systems. If you look at the metro map in the bus or somewhere, this is always a drawing of a graph. You have road networks. There you don't have too much freedom because the coordinates are already fixed, but still it's a drawing of some graph. You have power grids, you have telecommunication networks, you have circuits. If, for example, you look at the motherboard of your computer, you have a lot of peripherals, and they are connected somehow with circuits. And how to lay out these connections so that you don't use too much space. That's again a graph drawing problem. The thing is, we all think visually. If we have a complex graph and we don't have a good visualization, as we saw in the examples earlier, it's very hard for us to find things out. And having a good visualization can help us so much with the communication and the exploration of the network. The problem is that there are some graphs that are way too big that we cannot just draw them by hand. You can have graphs with hundreds or even thousands or even millions or billions number of vertices. For example, if you look at the social network of Earth, you have a few billion vertices. You cannot just draw that. So we have to find algorithms that can automatically create these drawings. And with that, we want to make networks more accessible to humans. And this is the topic that we want to look at here. We want to find algorithms that automatically draw graphs in some specific ways. So what are we interested in specifically? There are a bunch of visualizing variables that were defined by Jacques Bertin, and they are the following ones. We have the size, the shading, the texture, the color, the orientation, the shape, and the position of objects. And these are the most important variables that we have to consider when we want to define the visualization of some object. The most important one for us is the position. We want to figure out where do we place the vertices so that we can connect them in a good way. But also the shape is important, because we have different ways that we can represent vertices, and we have different ways that we can represent edges. It doesn't have to be straight line segments. It can be curves, it can have bends, it can be completely different. while the other variables, the size, shading, texture, color, orientation, maybe a bit, but those are not too important for us. That's usually done in post-processing. First we want to get some good layout, and then to make it very pretty afterwards you can add colors, you can add shading, but that is nothing that concerns us. We only want to find the positions and the shapes of the objects. For now, we will only look at the standard representation, which is the so-called node link diagram. So every vertex is a point in the plane, and every edge is a curve in the plane. Here, the graph visualization problem can be defined as follows. The input for us is some graph, and the output is a nice drawing of this graph. Well, this is just a mathematical description of what I said. Vertices are points and edges are curves. The big problem, however, is what is a nice drawing? And this is not something that you can clearly define. Maybe different people will have different preferences when looking at different drawings. And even for different graphs, one drawing style can be very good for one, but very bad for another one. So there's not the one answer. But what kind of properties should a nice drawing have? For that, we want to have a look at a few examples. One of the oldest I could find is the Tree of Virtues and Tree of Vices, which is from 1200. Here you can see you have all these virtues and vices which are represented as apples here on a tree. You can imagine every data point is one apple. And all these connections here, these are our edges. So this is a drawing of a tree. Today, at the end of the lecture, we will also start with drawing trees, which are some of the simplest graph classes that you can have. You have social networks or family trees. Usually when you want to draw your family tree, it's not always like this where you have the godfather at the bottom. Sometimes you have them at the top, like here in this drawing of Greek gods. You have chaos at the top, you have the children on the next level, and their children on the next level, and so on. So you can go through the family tree, figure out who is the child of which parents. And with a nice drawing like this one, you can get a lot of information out of it. Here we have a huge graph. This is the citation graph of the Graph Drawing Conference. So every vertex here is some paper that was at a Graph Drawing Conference, and every edge is where one paper cites another one. And you can see that you have huge clusters here, you have a lot of citation, so there's a lot of work going on. There is a lot of work building upon works of others within the community, and there's also a lot of collaboration going on. We have organizational charts, for example in politics. If you want to see what does the president do, what does the councillor do, what does the Bundestag do, and how are they connected to each other, then you can draw this as a graph like this one here. You even have some weird features like this. This is not something that you probably would do in a normal graph drawing, but it did have some layout reason here, because it says alternating down here. So alternatingly they do these elections, and that's why they chose to draw these edges here alternatingly crossing. The artist Mark Lombardi also created drawings of graphs. He wanted to document political and financial fraud by power brokers, and for that he built these networks and he drew them with circular arcs. This even defined a very special drawing style, which is called the Lombardi drawing. So these are some examples for social networks. We also have some for transportation networks. For example, the European high-speed railroads. You can just have the cities as vertices and all the railroads that go between them as edges. We can have the London Underground map. Here the stations are drawn approximately where they would be on the map, but you can also have a more stylistic drawing, and I think this one is much more readable, although this is more faithful. And if we get rid of all these additional information and we want to have a closer look at the graph itself, this contains all the information that we have here except the labels. And it's just a different drawing of this same graph. We use it a lot in bioinformatics. for example in the interaction between diseases. We can plot all these different diseases and have a connection if there is some interaction between the diseases. And you can see here that there are clusters. For example, different types of cancer, of course, are connected, but they are not so connected to mental retardation. We have molecular metabolic networks. This is the largest humanly drawn graph that we are aware of. At least in bioinformatics it is. And this is about the metabolic network of the human. And this was laid out by many students over many years. And from the broader view, it's very hard to see something, but you can zoom in to all these different parts and you will get lots of information out of it. And it's very well done. We have phylogenetic trees and networks. And there it's quite clear. You see, where do all these species come from? These don't necessarily have to be trees, but they are usually close to it. We have technical networks, very large-scale integration. Here you can clearly see all these small connections you have between all these different points, and getting a good layout where you can fit everything of this on the board, that's not so easy. You have transistor diagrams, you have wirings, you even have offshore wind farms, you have UML diagrams. All these are examples of graph drawing algorithms. There are temporal graph layouts, for example, storyline drawings. Here you have a drawing where you have one line for every character, and you can see throughout the story of Lord of the Rings, where are these characters and where are meetings between them? Where do they interact? So you can follow a single character through the story and you can see at which point does it meet with which other characters. If you have a 3D object, then you often represent it by polygons. So instead of having a real representation of the object, you take all these small triangles or quadrilaterals or whatever you want, and the more of them you have and the smaller they get, the closer you get to the real object. But you can also take what you get from there and represent it as a graph, because all these objects, they are just very small graphs that are connected to each other. We can have different styles of layouts even within a drawing of a single graph. So here we have a mix of node-link layouts, like here, and some arc drawings, where a vertex is not a single point, but here an arc. And it can even be more than one arc on the same cycle. So you can combine different drawings. You might have seen this type of representation already. This is a tree map. This shows you how large is this folder, and then recursively there is a folder like this, there's a folder like this, and you can see how much space do all these different folders and files take. And this again is a representation of a tree, because if you look at the folder structure on your computer, you have some hard drive and then you have some folders inside. So you have a connection from the hard drive to those folders. You have subfolders, so you have connections from folder to subfolder. And then you have files, you have connection from subfolder to file, and so on. Well, if you have symbolic links, then maybe it's not a tree anymore. Well, it's still quite close. On the hard drive, it is a tree, because you can go from top down and figure out where your stuff is. And we can have alternative representations. For example, here we flip it around. Instead of having a point for every vertex and a segment for every edge, we just make a circle for every vertex, and we have an edge if and only if they touch. This is a so-called contact representation. We will talk about this later in the course, I think in lecture 10 or something. If you want to see more examples, you can go to visualcomplexity.com. But now back to our problem. What are the requirements of a graph layout? We have some drawing conventions and requirements. For example, we can have straight edges, or we can have orthogonal edges. So we only have horizontal and vertical segments, but we have bands. These are things that we can define. We can say that our drawing has to be on the grid. So all the vertices and maybe also all the bends have to lie on the grid. But this is all optional. You can choose what you have. You can have without crossing, or you can have with crossing like here. This is all something that has to be defined. What drawing conventions do we want to look at? And what requirements do we have? Then there are aesthetics that we want to optimize. So these are hard constraints. It's something that we have to do. And now there's something that we want to do as good as possible. For example, we want to minimize the number of crossings like here. Here we have a drawing with 3 crossings. This has 0, so this is better. Or the number of bends. Here we have 1, 2, 3, 4, 5, 6, 7, 8 bends. And here in the drawing of the same graph we only have 4, so this is better. Or we want to have uniform edge length. Here we have one very long and a few very short edges, so the ratio between the longest and the shortest edge is very large. Here they all have the same length, so there it's very small. That means that this one is better if we have this as our aesthetic. Maybe we want to minimize the total edge length or the drawing area. This is a smaller drawing and this looks much more compact than this large thing here. Or we want to optimize the angular resolution. Here we want to maximize and not minimize. Here we have a very small angle, while in this drawing it's quite a bit larger. And we can look at the angle at edges at a vertex or at the angle between crossings. Again, we have a very small angle, we have larger angle, so this is better. Or we want to maximize the symmetry of the structure. And here we have a very nice example because this is a drawing where you don't have any crossings. But in this drawing you have 5 crossings. However, the symmetry and the structure is so much better than this one here. So I would prefer this one. But that is contradicting this crossing minimization here. So you can already see you cannot optimize all of them at the same time. There is not a single one that gives you the best drawing. It really depends on the graph. Here, allowing crossings makes it better. For other graphs, allowing crossings makes it worse. So this usually leads to NP-hard optimization problems. And then what you do is you look at specific graph classes. For that you can solve it. Or you look at different algorithms like approximation algorithms, where you only find something that is close to optimal but not optimal itself. So we have requirements, we have optimizations, and then we can also have local constraints. These can both be hard constraints, it has to be like this, or it can be optimization constraints, it should be as good as possible, or something completely different. For example, we can restrict that all edges have to be drawn upwards. Or we can have groups of vertices and edges that should be drawn closely together, so they should be clustered. So let's go back to the graph visualization problem. We only defined it for these node-link diagrams. But in general, what we want is we have a graph and we get some drawing such that our drawing conventions that we chose are met, the aesthetic criteria are optimized, and some additional constraints are satisfied. And this is the very general form of the graph visualization problem. And in this course we want to look at different conventions, different criteria, different constraints, and then try to solve this problem as good as possible. In the next part, we will go through some basic definitions of graphs. So if you are already familiar with them, you might want to skip the next part and immediately move on to part 4, where we talk about planar graphs and planarity. If you already know about those, then you can immediately go to part 5, where we talk about trees and the first drawing algorithms for binary search trees.